Now we're going into the definition of proportional, integral, and derivative. That builds off of our last talk, which we talked about the attributes of the error. To do that, we're going to actually go clear back to a very simple control type, which is called on-off control. I'm going to talk about on-off control, then I'll talk about proportional, then integral, then derivative. And then the next talk will be the interactions and standard forms of the PID. This chart will show up several times in this presentation, but it's just a summary. You can see that the controller type on-off is basically like a light switch. It's either on or it's off. Or a relay. It's either open, or closed or open. It's two states. And it operates off the presence of air. Whether the air is this big or this big, you're at 100 or 0% of your valve change. That's what we're going to talk about first, just to try to get this going, is the idea of on-off control being like a light switch, or a relay, or a contact closure. That's all, or a thermostat in your house. Your furnace, it's either on or it's off. It's not half on. So on-off control is a very simple two-mode kind of an output. And it's usually used in very large vessels where the dynamics are very, very slow. And you can see here I'm showing an example where I've got a tank. A large vessel, doesn't move very fast. So to get anything, you got to just turn the actuation device on 100% and starts up it goes. But what it ends up is you'll always have kind of an oscillation, up and down and up, but maybe that's good enough. So it's a very simple control. Actually, a lot of houses work off this. Your furnace is on, then you turn it off, then you turn it on, and so if you could trim the temperature of your room, it would oscillate. Maybe that's okay. If not, you have to go to a more elaborate type of control. Things about on-off control is it's inexpensive, and it's simple. It's either on or off. It will overshoot or have an oscillation, and it's designed for slow-moving processes. An example that I can remember someone showing me is like a bathtub. If you're sitting in a bathtub and you want to raise the temperature, you might turn the hot water on full blast, then turn it off. Where if you're in a shower and you did that, well, that wouldn't work so well because there's no capacity. So on-off has a place in very large where the control's you're allowed to deviate from the reference. Now, if you want to go beyond that, that's when we have to start understanding proportional. Proportional, its goal in life is to work on the change of air. And it's very important to realize that its goal is not to make the air zero. The goal of proportional is to make the change in air zero. That's an important difference, and I'll talk about that in just a second. If you can imagine like a knob, it's like in on-off you're either at 0 or 100. Well, with proportional, your output could be somewhere in the middle. So you have to have an actuation device that allows you to put it somewhere between 0 and 100%. Proportional control is designed to work on those types of devices. And in the simplest form, you'll see me put together block diagrams. This is what a block diagram looks like, where you have a set point and a measured value, and the difference is the error. That's this summation sign. The error is multiplied by a control gain, and then that control gain is usually, the control gain times the error is the output that goes to the valve. And I remember this is hardly used today, but in the early days, there was actually a knob that they considered a manual reset knob, because proportional only control would result in an offset. So if the measure was off, they'd go and adjust it and make it 0. And I'll show that here in a little bit. But you can see the fulcrum, this idea that the error is exactly proportional to the output based upon this gain multiplier. Some vendors will use the term proportional band. Proportional band and control gain are inverse of each other. So for example, a control gain of 0.3 would be a proportional band of 330. So that's one of the examples I can remember when I was running around doing this. I would talk to an E&I staff, so I need to put a control gain of 0.5. And he said, well, I never use anything other than 200. I mean, we were saying exactly the same thing, but he was working on a controller that operated in proportional band, and I was thinking in terms of a control gain that was a gain, not a proportional band. So it can be that simple that can throw things off. You have to understand the difference. This idea of a teeter-totter really helped me understand this idea of a fulcrum and a pivot point, where the pivot point really is your gain. If you had a gain of 1 or a proportional band of 100, it would represent how much of the output would move for a change in the measured value. So the proportional band says, I have to have 100% change in the error to produce 100% change in my output. Same thing with a gain of 1. That means any little change, they're equal. Okay, that's the middle point. You can see over here, if I jam the gain over to be greater than 1, you can see that the error doesn't have to move very much and the output moves a lot. You might think in terms of a large actuator change results in a small process change. So in terms of process gains, you have a very small process gain because it takes a big actuator change to get anything to happen. That's kind of what I'm showing here. If you look at the circle here, is if I had an error, just pick a change in error, the controller has to be greater than 1 to give me an output that's much bigger. In order for that output to zero this error, the process gain is what absorbs the change in actuator. So the actuator change may be large, but it may give me a very small process gain. Kind of like the garden hose. If you want to fill a bucket, you have to open up the garden hose a lot to get anything to happen. That's kind of what we're showing here. You have to have a large gain to get that process to move. But the goal is to get the change in error to stop. So how much does the output have to change? So you can see that a large proportional gain is aligned with a small process gain. And so you can see right here is the change, in order for the bookends to be equal, this relationship. So I'm kind of leading you towards tuning rules. And you'll see when we get to tuning rules that the controller gain and the proportional gain are actually inversely proportional, which is what you can see here. Now, if I flip the other side and do the example where now I have a gain of less than 1. So proportional gain of less than 1 means I have a large error. You can see here I have a huge error, but it doesn't require a very big change. So that's like the fire hydrant. Just a little bit of change and it has this huge impact. So it's like the strength of the actuator. If I have a really strong actuator, I don't need to move it very much to get a big change. Again, the bookends here. I have a big error, but I don't need to move the output. This again is like, if I've got a bucket and a fire hose, I just barely open it and it'll fill it. Okay, so that's what we're seeing here is a little change results in a lot of output. So that's where you can see this fulcrum. It's pivoted on the one side. So that's how I like to think of proportional control. Is literally it's like this teeter-totter, and it's trying to say, okay, I got to change an error. I have to make the output such that the measurement will move exactly how much the error moved. The process gain is the way that you normalize it. And that's really important, is the controller gain and the process gain have to be inverse. And you'll see that as we go through a little bit further on. So as we end up on the proportional, what you can see here, and then I'll show you an example of why reset can occur. But what we've got here is an error. And you can see proportional means a couple things. Not only is it that teeter-totter, it is the output is proportional to the shape of the error. So here you had an error that looked like a step change. So here if a gain's greater than 1, the output's bigger. If the gain's equal to 1, they're matched. If the gain's less than 1, it's less. So the output is proportional to the error. And the gain is what's adjusting the proportion. And we're finding that you need to bias the gain with the process gain. And we'll talk about that when we get into tuning rules. Now, why isn't it used everywhere? Well, if you use it, it actually results in what's called an offset. And the best way to show that is this tank example. So here what I have is you can kind of see this tank. There's water flowing through it. So this is like a constant flow. And this is a little float. And this float is connected to the actuator. So as the tank goes up and down, your actuator goes, so they're proportional. And the fulcrum, literally, it's a mechanical fulcrum. So you can kind of see how that proportionally would work. Now let's say this is running along, this is my reference, and then somebody opens this outlet flow. Boom. So now I have more flow going out than going in, so the tank level starts to drop. And what's going to happen is the proportional control will stop the tank from getting any worse when the inlet flow and the outlet flow are equal. That's called a balance condition. So it actually is trying to get the actuator to move until the inlet flow and the outlet flow are equal. When that's happened, proportional says, well, look what I've done. I've just stopped this thing from getting any worse. But where did I end up at? I'm no longer at the set point. So that's what's called an offset. And I've seen people, they'll inadvertently block the integral term, and they'll be the set point and the measured value, or they're just offset. And usually that's my first question, did you block the integral? So this is what can happen. So there are some cases where if you have a loose tolerance, this is fine. Today's applications, this is becoming more rare. So what would have to happen to make this work? Well, you'd have to take that ball and stick it further down in the water to open the valve further. So that you'd have to have more water going in than going out, and that would cause the level to come back up. Oops. And when you got it back up, you would be back at set point. That's beyond the capacity or capability of an integral controller. So that's just not going to happen with P only. So proportional only will result in an offset. That's where the integral term comes in, and that's what we're going to talk about now. So on-off is the presence of air. Proportional, it's the change in air, but you'll result in an offset. Integral is the next one on the block. It deals with the duration of the air, and its goal is to make the air zero. So with integral control, the output is based on the duration of the air. The calculation of the average air over a period of time is roughly what that integral thing's doing. And as long as an offset exists, the output will not stop changing. It will just keep going. Some people call it like the watchdog. Another term for integral is reset, and I'll talk about that here in a little bit. In terms of a block diagram, this is what it looks like, where you have the set point and the measured value become an error. The error gets worked on with this integral term. Remember, the integral term is a calculus term representing integral. It's a math function so that you can see that represents calculating the area over time. That's all that is. And this gain is just a multiplier. So it's literally changing the area over time slope. And I'll talk about that in just a minute. So when we run here, this represents the error. So I had an error as the set point minus the measured value. So for a period of time, so if I take this time, that green area would be the area under the curve. So at time 1, if this is a y-axis is area and the x-axis is time, at time 1 I have area A. At time 2 I now have area B. It's continuing. The error is not going away. And at time 3 the error continues. So if you look at this, the output would be proportional to the area under the curve. That's what that mass symbol of integral means. Now, what the integral does, the gain is simply a multiplier. So if the gain is less than 1, you reduce the slope. If it's equal to 1, then that is exactly the area under the curve. And if it's greater than 1, then it's very, very steep. So with integral, so what you have to think about is, well, what's integral going to be proportional to? And the best way I can explain that is like the mass of the device. If you have a device, that's heavy, you don't want to make the output move faster than the device has the ability to respond. Otherwise, you'll wind up, or your output will change faster than the process can move. So what you'll see here is if you have a really light process, then you could get away with getting the error to 0. So think about how fast could this process move so that the error could go away. That's what this gain has to be proportional to. So the integral time is related to the mass of the process, and the mass of the process is typically defined by the time constant. So we'll see that here in just a minute. When I compare proportional, remember proportional is going to give you this, what they call this P kick. Boom, you get for a given error, I have 3 different gains. You can see what would happen. But with integral, it's very slow to respond. So here you can see when the error first happened, proportional took off on it, and then it said, I'm done. Where with integral, it said, well, it's still there. So over time, the integral can become a very powerful component. Now, the next one on the list here is derivative. So derivative is dealing with the rate of change of the error, and its job is to slow down a changing error. So what we're going to do here is we've gone through on-off, we've gone through proportional and integral, and then we're going to talk about derivative. We'll do the same thing with a block diagram, and then we'll talk about how they all interact. Now, I used to not resemble that guy. The derivative mode of the controller is an enhancement to the standard PI controller. Typically, you won't find derivative by itself. It usually comes with the PI control. So, but we're going to try to explain derivative by itself, and then I'll show you how they all work together. This mode adds to the controller output a value that is proportional to the rate of change of the error. In other words, what it's trying to do is saying, based on the slope, here's where I think the error is going to go, so I'm going to fix it now. So it literally anticipates where you're going to go. It's trying to predict where you're going to go and then fix it now so that you don't go there. This picture really illustrates what we're talking about. As you can see here, that now is the current time. And so it's saying, based upon my last measurement and now, the last two samples, I'm going to calculate a slope. That's the derivative. So you're calculating this derivative based on the current sample and the last sample, and then you're extending it out. So the time that you go out into the future is referred to as the derivative time. So it's like, well, how far into the future do I expect my prediction to be accurate? Now, in this case, would you say this is saying that this little, what I'm drawing right here, represents the future error. Based upon the past errors, is that an accurate prediction? That's the problem with derivative, is in the original days when derivative came out, there was a lot more pneumatic instrumentation, there wasn't a lot of noise. So the last sample was a good indicator. Think of driving a car and you're on a road with a very large radius. And remember, you can't make an adjustment by looking out the front window, you got to look out the back. So if you could recognize that the road had a slow turn, you could probably compensate to keep yourself from going out in the field. Now imagine you're going down the road and it's a 90-degree turn. I mean, you're already out, you know. So the problem is with today's things, process dynamics are much, much faster, which makes derivative even more difficult to use. And those are some of the considerations that I'll show you. A lot of times they say D stands for disaster, never use it. It's not always true, but it's more true than not. And I'll show you how derivative can be used. So this is an example of a loop. Notice there's no noise on it, which is not very realistic. But it's saying if I had a set point and I had a step error, and I'm not showing that here, but the controller measurement were to catch it and bring it back. So the proportional and integral control would have recovered the disturbance. Now everybody says that's good, and then they say, well, that took too long. Well, this is where you could work with derivative in this instance to speed up the response. The way you think of derivative is a lead action. It's adding it's trying to make this, imagine you're in your car on a cold day, and when you got home from work last night, you had the heat just perfect. Well, then you get up in the morning and you're like, well, I know eventually the heat will be right, so I'll just leave everything alone. Most of the time you get in the car and you turn everything up and you turn the fan on until the heat starts coming, and then you start backing it off. Well, what are you doing? You're trying to speed up the natural tendency for the automobile to warm up. That's what derivative's trying to do on a process, is make it respond faster than it normally would. They call that a lead action. And there's pluses and minuses, and of all the loops I've tuned, I've only used derivative a few times to really dial in the lead action. And I'll show you that when we get to it. This is a block diagram, not a block diagram, this is a chart, just to show or summarize what we've talked about so far. With proportional, you can see here's a step change, and really this is a pulse, but it's two step changes. So you can see if you have a step change in your error, you'll see here that the proportional is proportional to that. The integral is the area under the curve, and the derivative is a pulse, basically. Over here, you can see that's what it would look like. That's what I would recommend you to do right now is draw a couple of waveforms. Draw a sine wave and figure out what these would look like. Or better yet, draw a triangle wave. You know, and what would this look like? That really helps you understand proportional, integral, and derivative. What would the proportional look like? Let's say this was a triangle wave. What would proportional look like? What would integral look like? And what would derivative look like? I would recommend that you do that before we go into the next section. So to finish this is we talk about on-off controllers. It works on the presence of air, but you're going to result in a limit cycle. Proportional only works on the change in air, and its goal is to stop the changing air, but by itself you result in an offset. Integral is a watchdog. It works on the duration of the air, and its goal is to make the error 0. But integral by itself it doesn't give you that fast kick, so it's always behind. So you'll result in an oscillation with integral only. Derivative is really an enhancement to the PI algorithm, so you would very rarely, I can't think of an instance where you would ever use derivative by itself, but it's a lead action to try to anticipate where the process is going and make a correction before the error gets out of hand. That is, in general, at I'm trying to reduce the complexity of the problem to say there's on-off, proportional, integral derivative that works off the attributes of magnitude of error, duration of error, and rate of change of error. That's the fundamentals of PID, regardless of whether it's standard, parallel, classical, whether it's proportional band, integral time, integral gain. That's the fun stuff we're going to cover next.